Alright, Michael, I'm going to show you how to do this parametric thing. Alright, so you know an epicycloid is like where this circle is like rolling around the other circle. So excuse my poor drawing. So I kind of drew what it's supposed to set up like. And let's say there's a point here. We'll call that point P. Alright? So a couple things we know about these circles. That this radius is 3, the bigger one, and this radius is 2. So let's say, I know it doesn't look like it, pretend these are touching, there's no space between them, it was just my bad drawing. Let's say we drew a line and connected these two, alright? And then let's say I drew a line between these two. So we have a line connecting the two radiuses, the two centers of the circle, and a line from the center of the smaller circle to the point P. All right? And the next thing we have to do, we have to define some angles, which is fun. So let's pretend that we'll call this angle here, call that theta. It's a pretty basic angle name. And we'll call this angle here alpha. So I know this is pretty useless right now, so what we're going to do first is draw some triangles and get some stuff set up. So let's go ahead and do that. All right, let's pretend this is a triangle, that dash line, and let's pretend this is a triangle right here. We got these two areas. And we'll work with some trig and get some definitions going, all right? So let's start over here with the bigger triangle. All right. So we know from the bigger triangle, we know that this angle is theta, and by the same definition, if you know your geometry, you know that this angle is theta as well. And so let's define some sides. So we want to define the hypotenuse, which is really easy. If we look at our circle, we got the big one whose radius is 3, plus the smaller radius is 2. So 3 plus 2 is 5. So our hypotenuse is of length 5. So now what we want to do, we want to define this side of the triangle and this side of the triangle in terms of theta. And if you know your trig, you know that sine of theta is equal to the opposite side, which we'll call y, because it's going vertical, over 5, which is the hypotenuse. And then we know cosine of theta is the adjacent angle, which we'll call x, over 5. And I'll label the sides here too. X and y. All right. So if we solve for x and y, we get x equals 5 cosine theta, and y equals 5 sine theta. All right. So if I redraw my triangle with everything labeled, this is what I get. Sorry, you can't see what I'm drawing. I'm drawing it in. Okay, here. We got 5 sine theta, 5 cosine theta, and theta, and there's our 5. So there's our first triangle. All right. We'll come back to this later. All right, we'll go to the second smaller triangle. All right. So let's talk about some things we know. First, we want to find an angle. And if we remember from our picture, if I draw a vertical line, and then we add this line, so we know that this angle here is theta, and we know that this angle is alpha, right? And by geometry, some theorem, I can't remember, we know that this angle is these two added up. So this is theta plus alpha. That's that angle there. And the other thing we know is that the hypotenuse is the radius of the circle, which is 2. So I'm going to redraw the triangle. I'm sorry. Sorry, you can't see what I'm drawing. Right. And so what we want to do is we want to define the triangle in terms of this angle, theta plus alpha. And if you just think about it from the same one, since this is the opposite side, we get opposite and sine's opposite over hypotenuse. We get 2 sine of theta plus alpha. And then by the same token, we get 2 cosine theta plus alpha of the other side. So this is that side, that is that side. Right now, so we have our sides defined, and these will come into play in a second, but first we need to define what's alpha. And I don't know if you've done any of this kind of stuff, so I'm going to draw another picture of a triangle at more of a close-up. So let me draw it real fast. Right. All right. So if we look, I drew right where like the circles are touching. And so we have our angle theta, and we have our angle alpha. And now this is a kind of theory. So since the circles are unrolling on top of each other, that means the arc lengths, and arc length is just the like the snippet of the circle. They have to be the same since the circle. They're not like the circle. The smaller circle isn't sliding on top of it. It's merely rolling. That means that these two lengths right here, these two lengths, these curves have to be equal in length. And we define arc length by a cursive L. So I'm going to call this LA over here for the big circle, and I'm going to call it LB for the smaller circle. So therefore we know that LA equals LB. Right? Okay, now we need to know something about arc length. So if we have a circle with radius, okay, let's say I have a circle, and it's of radius r, and there's an angle theta, so this arc length right here, which we'll define as L, L equals the radius times the angle, r theta. So in this case, we know that this radius is 3, and that radius is 2. So, and we can use our angles theta and alpha, so we're going to get, for A, we get 3 theta equals 2 alpha. And from here, to get in terms of theta, we solve for alpha. So we get 3 halves theta equals alpha, like that. So there's our alpha. And the reason we solve for that is that now we're going to plug in here. I'm just going to drop here. So you get theta plus alpha in this case equals theta plus 3 halves theta. And we can simplify that into 5 halves because 1 plus 3 halves is 5 halves. 1 plus 3 halves equals 5 halves. So we get equals 5 halves theta. That's alpha. So when we can rewrite these sides as 2 sine of 5 halves theta. And like that. Sorry, I didn't know if you saw it when I wrote it. And 2 cosine 5 halves theta. Now, all this crazy busy work. Now I'm going to show you why we did it on a different page. It's a little bit cleaner. Let me rewrite this or draw the circles again. Excuse me, my drawing's not very good. I'm sorry. Now I'm gonna draw the triangles in a little harder. So here we go. If you look, we want to find exactly where this point P is. That's the point. Now, if we think about it, this length down here, the longer one, minus the shorter length of this triangle, of the little triangle, is the x-coordinate of the p. And in the y direction, we take the longer one minus the shorter one gives us our y direction. That makes sense, because that'll give us the y direction of our p and the x. So let's start with the x. Let's say I just label these sides. I'll draw the triangle over here, like something like this. Let's say I call this side A, and then the tiny one is B, and then the big one is C, and the tiny one is D, like that. Okay, so we know in the x direction, we'll call it x of p because that's what we're solving for, the p's thing. We know it's A minus B, and in the y direction, it's C minus D. Now, all that work we did on the other page is that we have our A's and our B's now, but they're in terms of theta. So if we look, our A and our C are right here. So this is A, and that's C. And if you look over here at our B and our D, this is our B, and this is our D. So B and then D. Okay. So for the x direction, we need A minus B. So A is 5 cosine of theta, and then we have our B, which is 2 cosine of 5 halves theta. So now we're writing in terms of theta, because that's our variable for a parametric equation. So x of theta equals our A, which was 5 cosine theta, minus our B, which is 2 cosine 5 halves theta. So that's one of our parametric equations. Now let's do it in the y direction in the same manner, which is C minus D. And the only difference between the y and the x, if you notice, is just there's a sign instead of a cosine. Right? Okay, so I'm going to write it, 5 sine theta minus 2 sine 5 halves theta. And that is how you solve the parametric equation. And all the parametric equation is, you get x and y given different equations by a single variable, which in this case is theta. And that was really complicated, I know, and I hope this helps. All right, see ya.